Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on Advanced Transition Metal Organometallic Chemistry. Today we are going to be discussing transition metal cyclopentadienyl carbonyl complexes and their reactivity. So, these transition metal cyclopentadienyl carbonyl complexes are more popularly called as half sandwich complexes. The name derives from their metallocene counterpart, which contains cyclopentadienyl metal complexes and referred to as sandwich complexes, whereas these compounds transition metal cyclopentadienyl carbonyl complexes are referred to as half sandwich complexes. So, in our last class we have looked into various methods available for preparation of these half sandwich transition metal cyclopentadienyl carbonyl complexes and also we have looked into their reactivity. Primarily of the synthetic routes that are available for preparation of these complexes involve direct reactions of metal carbonyl with cyclopentadiene ligands, or the reactions involve metal carbonyl metallates with cyclopentadienyl reagents in presence of oxidizing agents. Also involves the reaction of cyclopentadienyl transition metal complexes with the carbonyl compounds in presence of reducing agents, or direct reactions of metallocenes with carbonyl compounds, or by just simply heating of metallocenes with carbonyl compounds would yield these half sandwich transition metal carbonyl complexes. We have also looked into the reactivity of these compounds, and what we found that the reactivity of these compounds depends on the nature of the carbonyl moiety. The carbonyl moiety can act as a bridging ligand or also act as a terminal ligand, and it turns out that for dinuclear complexes of 3D metals which are smaller in size, both the bridging and terminal carbonyls are observed, whereas for such complexes of 4D and 5D which are more bigger in size, only terminal carbonyls complexes are seen. So, with that today, continuing further on this discussion, we are going to be talking about the reactivity of transition metal cyclopentadienyl carbonyl complexes. So, one of the main thing is the reduction of such complexes. Example is Cp vanadium tetracarbonyl in presence of sodium mercury eliminates CO to give disodium Cp V CO3. Furthermore, the reaction of Cp Fe dicarbonyl dimer, again the reduction with sodium mercury gives the metallate sodium Cp Fe CO2. Now, that upon reaction with methyl iodide gives the methyl derivative Cp Fe CO2 CH3 along with the formation of sodium iodide. So, this is an interesting reaction in which the dimer is Cp iron dicarbonyl dimer is reduced to give this metallate, which then furthermore is alkylated to give to make the methyl derivative, which is cyclopentadienyl iron dicarbonyl methyl along with the formation of sodium iodide. So, certainly a reduction is an important reaction for cyclopentadienyl metal tricarbonyl complexes. Similarly, the reaction with dihalogens makes the iodide complexes. Gives the halide derivative. This is illustrated by the reaction over here, Cp Fe dicarbonyl dimer plus X2, X equals bromine iodine, giving 2 Cp Fe CO2 X, that reacting with AlX3 CO gives Cp Fe CO3 X. Now, what we see over here is the formation of the halide and subsequent abstraction of the halide to give this Cp Fe tricarbonyl cation, and the vacant site so generated by the abstraction of the halide is occupied by the third carbonyl. So, many of these times even CCl4 and benzyl chloride and PHCH2Cl can act as halogen source under photochemical conditions. The other obvious reaction for this half sandwich cyclopentadienyl metal tricarbonyl complexes are the electrophilic ring substitutions. So, like in ferrocene, similar to ferrocene, these complexes readily undergo electrophilic ring substitution at Cp ring, and the examples of these are CpV CO4, CpMn CO3, CpRe CO3. So, this is something which parallels the reactivity seen in ferrocinyl complexes, where two electrophilic substitution was facile at the cyclopentadienyl ring, and even in half sandwich cyclopentadienyl metal carbonyl complexes we see the same trend happening, that the electrophilic substitution at the cyclopentadienyl ring is also facile. Obviously, the reason behind the same is also similar, given the fact that cyclopentadienyl anion is electron rich carbanionic and has partial negative charge. Hence, it is no wonder that these ligand undergo electrophilic substitution reactions similar to that observed for ferrocene or other metallocene complexes. Now, having said that, one should also think that whatever restrictions which held good for electrophilic substitution for ferrocene should also be holding good over here, and that is that the electrophile cannot be acting as an oxidizing agent or somehow oxidize the metal center of these half sandwich complexes. Obviously, in that case electrophilic ring substitution might not occur. So, as far as the substitutions are concerned, actually there are two kinds of substitution that might happen in such kind of complexes, which are CpM CON. The substitution can happen at the Cp ring, which was we are just talking about electrophilic ring substitution. The other possibility is substitution occurring at the CO, and we are going to see how that affects. So, substitution this is illustrated by this example of manganese, which is CpMnCO3 reacting with L, giving CpMnCO2L plus CO. Similarly, Cp cobalt CO2 reacting with L, giving Cp CO L2 plus 2 CO. L can be phosphine, olefin, L2 can be diolefin, okay. And this reaction generally is accelerated by thermally or photochemically. So, requires thermal or photochemical activation. So, we see that this Cp manganese carbonyl complex is being heteroleptic in nature. Substitution not only at the Cp ring can be invoked, but also substitution of the carbon ligands can also be done, and this is by replacing the carbonyl with other dative ligands like phosphines, olefins or diolefins, and the process would require temperature or photochemical activation. Now, we had spoken about oxidative dimerization in our previous class that spoke about how compound was dimerized as a result of oxidation by using an oxidation agent. Here today we are going to look at another such reactions or related reactions, which is oxidative decarbonylation. So, the reaction involves the reaction of Cp star rhenium tricarbonyl reacting with hydrogen peroxide 30%, leading to elimination of 3 carbonyls to give Cp star rhenium trioxo compound in 70% yield, which in presence of phosphine gives corresponding phosphine oxides to give this dimer. To give this dimer, the opposing reactions, if we take the dimer and react that with oxygen, give this rhenium Cp star trioxo compound, which in presence of high CO pressure in THF at 25 degrees centigrade would give back this rhenium tricarbonyl compound. So, this is an interesting compound in which the rhenium is in +7 oxidation state, and it also proves the fact that these cyclopentadienyl rhenium complexes also occur for higher oxidation states of the transition metal. Usually, the CP complexes by and large that one encounters occur for low oxidation state of the transition metal, but here we have this rhenium compound tricarbonyl CP star rhenium when oxidized with hydrogen peroxide produces a CP star complex of rhenium containing 3 trioxo species, in which the metal center is in +7 oxidation state, and that is kind of interesting. Subsequent reaction of this trioxo CP star compound with triphenyl phosphine would give this rhenium oxo, bleaching oxo, as well as terminal oxo rhenium CP star dinuclear compound shown over here. So, with this we sort of covered the topic of CP star transition metal carbonyl complexes, and we will move on to look at another interesting topic, which are CP star transition metal nitrosyl complexes. So, instead of carbonyl complexes that we have been talking about, now we are going to be talking about cyclopentadienyl metal nitrosyl complexes. Now, nitrosyls are usually called NO ligands, and the nitrosyls are a versatile ligand because it functions in 2 ways. A very versatile ligand which can function in 2 ways. What are the 2 ways? One is as a coordinated NO plus cation, as a coordinated NO plus ion. This, in this state, it is isoelectronic with CO. Or as a coordinated NO minus ion. In this case, it is isoelectronic with O2. Now, interesting thing about NO is NO can bind in a linear fashion as well as in a bent fashion, and this is illustrated over here. For example, Ln metal M, if this is a 17 valence electron species, can bind with NO to give Ln M plus 1 N So, this is NO as one electron ligand and bent angle MNO. So, the metal complex over here has become 18 valence electron by virtue of getting this one electron from the NO. Similarly, NO can also bind as a 3 electron donor. In that case, it loses an L, and the resultant n minus 1 M, the oxidation state becomes minus 1 N O plus. So, it will have a conformation of this type. This is minus 1 and this is plus. So, overall it is a neutral molecule, and then it also has 18 valence electron configuration, NO as 3 electron ligand and linear angle of MNO. So, what we see is that NO can bind in two ways to metal. It can form a 1 electron bent, where the angle is bent less than 180 degrees, whereas it can be linear. This angle will be equal to 180 degrees. So, this is the linear binding, and when it is a linear binding, it is a 3 electron donor. As a result, one of the dative ligand bound to the metal is lost, and that is replaced by the electrons from the NO. So, basically what it proves is the versatile nature of the NO, the way it can bind to the metal structure. Now, with respect to the linear to bent structures triggered by 2 electron transfer from the metal, the linear structure MNO to bent structure MNO conversion in nitrosyl complexes is triggered by intramolecular transfer of 2 electrons from metal to ligand. And also, as a result of this, a vacant site is generated, and that results in associative substitution. So, upon which a vacant coordination site is generated, and associative substitution becomes possible. So, because nitrosyl ligands can be a 3 electron donor as well as 1 electron donor, because depending on the way it binds. So, isoelectronic complexes complexes is possible by substituting 3 CO ligands with 2 NO ligands. Also, one CO ligand can be substituted by one NO ligand with introduction of a positive charge. So, with this I would like to bring upon the conclusion of today's lecture. Today we have spoken about two different kinds of half sandwich complexes. These are transition metal carbonyl complexes as well as transition metal nitrosyl complexes. With regard to transition metal carbonyl complexes, we have looked into various synthetic methods available for preparation of these complexes. Also, we have looked into the structure which are observed for transition metal carbonyl complexes in the beginning of our lecture, and what we had seen that this carbonyl moiety can act as a bridging and terminal ligand depending on which kind of metal center they are binding to, and this is very much observed in dinuclear complexes where bridging and terminal modes for the carbonyl moiety are observed for the smaller 3D metals, whereas terminal carbonyl moieties are observed for dinuclear 4D and 5D metals. So, as far as the other half sandwich complexes are concerned, these are transitional metal nitrosyl complexes. We have seen that the nitrosyl ligand are a versatile form of ligand because they can bind both in as a 1 electron donor as well as a 3 electron donor, and depending on their types of binding. For example, if it is a 3 electron donor, they show linear binding, whereas if there is 1 electron donor, they bind in a bent fashion. Also, what we have learned in today's class is the fact that in isoelectronic complexes one can sort of envision to substitute COs with NOs, and if they want to do that, they have to keep track of the electron counts. For example, 3 COs which will have 6 electron can be substituted by 2 NOs which will have 3 electrons for each of the NO. So, eventually they would be isoelectronic. Similarly, one can substitute 1 CO by 1 NO, but with the introduction of a positive charge. So, hereby what we see is that these ligands for in isotopic species, COs and NOs or the CO counterpart or the corresponding NO counterpart can be equally possible to synthesize based on the electron count alone. So, we are going to continue further our discussion on these transition metal nitrosyl complexes, particularly looking at various preparative methods, their structure bonding and also their reactivity in the next class. So, till then, goodbye to you and I hope to see you in the next class. Thank you.